Yeah, so let's get started off. So in the last lecture, I was talking to you about the structure of disks, the standard, option for storing data in a non-volatile manner. And basically, what we observed is that disks will offer a, a good option where we have random access to the blocks. A block is a unit of transfer, data transfer from the disk to the main memory, and these are random access devices. So you give a block address, and the disk controller will be able to give you a block of data, which is usually something like half a kilobyte to about 8 kilobytes of data into memory buffers. Now, we also seen that the amount of access time that is required to access this block involves the so-called seek time, where you have to position the read-write head onto the cylinder from which you are reading the block, and then the rotational delay for reading off a particular block from the from the surface when it is spinning. Okay, so we've seen all this. Now, what we're doing is to see that if when there is a file, the file has records, and we need to now store this file onto the disk. So what we will do is to pack these records into block units, and then map those. Then we'll get one sequence of record units. So we call them as file blocks, and then these file blocks need to be mapped to the disk. And so we were looking at what are the mapping policies that are possible here. So one of them is to do what is called contiguous allocation, where we will where we will map the consecutive file blocks onto consecutive disk blocks, consecutive file blocks onto the consecutive disk blocks. Now, the advantage of this is that if you want to do a scanning of the entire file, it can be done very fast, because the file blocks are all on the consecutive disk blocks. So we have seen the notion of consecutivity. Basically, consecutive means from an access time point of view, these blocks that are there on a certain one particular cylinder are said to be close to each other, right? And then the next cylinder, etc. Next adjacent cylinder. No, but the downside of this kind of a contiguous allocation is that when you're trying to include a new block into a file block, actually into your file data, then that file block has to go into a, since our policy of storing consecutive file blocks and consecutive disk blocks, somewhere in the middle that new block has to be inserted. So if you have to insert a new block somewhere inside, in between several other blocks on the disk, then if you're roughly trying to insert it in the middle, then it involves reading off half the blocks of the data file and writing them back, which is a very costly operation, right? So first of all, reading itself is yeah. So, and then reading so many blocks is a lot of cost. Okay. Then on the other extreme spectrum, we have this linked allocation, where each of the file blocks is actually stored on some random disk block, and then in order to find out where the next block is, of next block of the file block is lying, from each of those disk blocks we will have a pointer to the block where the next file block can be found. Okay, so that's what is called each file block is assigned to a some disk block, and from each of these disk blocks we have a pointer to the next block that contains the next file block in the sequence. Of course, the file expansion would be very easy in this case, right? So all that you have to do is to actually do standard linked list insertion. So in some sense, what is happening here is that the file block, which is an array of blocks, is actually made into a linked list on the disk. Okay, it's a singly linked list on the disk. So the pointer is the disk pointer. So that a disk pointer is nothing but the disk address. The disk address has surface number, cylinder number, and block number. So these numbers are, so it takes about 10 bytes or something. Right? That's the disk address. So this disk address will be stored in each of these file blocks, so that you will be able to find out where is the next file block lying on the disk. Now the expansion, of course, is very easy, because you know that inserting a new element into a linked list is easy. Right? You can do pointer manipulation and then insert a block. Whereas, but the downside of this is that if you have to access the first 100 blocks of a file for some reason, then it will involve chasing 100 disk pointers, right? So each of them might potentially include again seek time rotational delay. That's it. Okay. If your file blocks are consecutive disk blocks, then you would hope that the disk accesses have less amount of seek time involved, because they are on the same cylinder. So the scanning can become pretty costly operation. So you can also, of course, think about some kind of a mixed allocation, where we say that, okay, I'll take first 25 blocks of the file sequence and then put them in consecutive blocks, and then the next 25 I will put in some other consecutive place and put a pointer from the first 25 to the next 25. You can take a policy like this, where you use mixed allocation, where you use contiguous chunk of disk blocks for some part of the file and use again put a pointer, and then the hope is that when you are trying to insert a new file block, then it's kind of easier. You don't have to read and write lots of disk blocks. You only have to read the disk blocks that are involved in that particular segment in which this new block is going. Okay. So mixed allocation is also possible. Now, this is how the sequence of records in our course, the files that we are dealing with are essentially sequences of records, right? So these records, of course, can be need not be directly the tuples of the relations that we are talking about. They could be something which may have some extra information, or they could be longer than these records could contain multiple information about multiple tuples, etc. So it's possible. But so you remember that we long time back we discussed what is called physical data independence. So the ability to kind of change the organization without affecting the logical view of the data. Now, so all this would be possible if we have appropriate mapping information as to how those relations are realized on actual files of records. Okay, so that information as to what is the file and whether that file has, what is the information about that file which realizes this relation. Is it one file or is it two files? Is this couple sequence? So all that information will be there in a uh, uh, in a uh, in some sense a metadata kind of store, and so you have to consult that before you can actually make use of this file for actual data access. So first the file headers will be retrieved, and then you get this information about what is there in the file, and then whether there are what we call as access structures, additional. So we're going to discuss what are called disk data structures. We have seen normal data structures, memory data structures, and data structures. Now we're going to see disk data structures. And so these data structures will completely lie in the disk, and so you need to know as to whether there is a available data structure for faster access for records of this file, etc., and then make use of it, how to make use of it, and all that. We'll come into picture. Now, let's see. First thing is, let's look at what are kind of various operations that we may have to do on files from our perspective, from the database perspective. Obviously, inserting a new record. If there is already a bunch of records are there, you want to insert a new record into the file. Now, depending on how the particular file is organized, which we are going to discuss in a short while now, this may involve actually an appropriate position to involve appropriate location where this new record has to go into the file. Okay. So we will see. So this will become clear when we discuss what are called file organizations, how are files organized. Deletion of a record, obviously. So deletion of a record involves first locating the record. Where is it exactly? Which block of the disk is it? So that might involve some kind of search, and then delete that particular record from that block. It may involve movement of other records in case there is a policy about say contiguous allocation or something. Updating a record field or fields is in some sense equivalent to deleting the old record and inserting a new record. And then search for a record. So given some value of the either the key field or the non-key field, etc. Given values of some of these fields, you have to locate either a record or records that have this specific value for those fields. This is a very often required operation on files. And then range search. So we may get two values for the either the key field or the non-key field. And then we will be requested to get all those records that have values between these two minimum and maximum values that have been given. The range has been given. So that's called as the range search. Now, how successfully we'll be able to actually carry out these operations will crucially actually depend on something called the organization of the file, and also whether there are any indexes available for the file. Indexes are additional access structures that we are going to discuss, whether any indexes are available and what is the organization of the file. How are records actually placed inside the file. So now, depending on how the records are placed inside the file, some of these operations actually might be easy, some of them might be tough, etc. So we will see examples of that. Okay, so that brings us to what we call as primary file organization. The primary file organization is basically some kind of a logical policy that we use, a method that we use for placing records into file blocks. What is the method? Let's look at, for example, a student file. We might want to organize this file as a sorted file in increasing order of the roll number values. We know that roll number is a key for the student records. So we might take a logical policy here of organizing these records of the students in increasing order of the roll number values. So this is an example file organization. So this is a sorted file because they are in increasing order of the roll number values. In general, the goal of a file organization is essentially that how do we ensure that the operations performed frequently on this particular file execute fast. Okay. So as you can see, for example, in this case, suppose we have organized the file like this, then there may be a so roll number based access will be pretty fast because we can exploit the sorted nature of the file and then get hold of the record that has a specific roll number, given roll number, we will be able to quickly get that. What if you ask you give a name and ask for a record that matches this particular name of the student. So we don't have any other we don't have any means other than scanning the file and then start from the first data record and then keep on searching for this particular name and then find out all those student files that have matching values with this name. So if you now say that okay, my access to the student records by roll number and by name are both frequent, and I would like this organization to be in such a way that both of them actually are pretty fast. So in some sense, it's a if you organize it by roll number values, then this is a conflicting kind of data access, right? So if you choose to make roll number access fast, then the access based on name might be slow. So what we do typically is to first choose some one primary file organization using which we can make one of these accesses fast, like for example roll number, and then to make the other access fast, say name access, we will construct a additional access structure. Okay. So we will basically we will construct a separate data structure that will take this name, using which we can actually use the name and then search through that structure and then get hold of the roll number or get hold of the pointer to the particular block in which this set of students are lying. Okay. So those things are what are called index structures, and we will see those details later. So let's first look at what are the various options we have for file organizations. Okay. So this is let's look at the options that we have. So we will discuss what are called the heap files and sorted files and hashed files. Okay. Heap file is actually a file that doesn't really have much of an organization. It is like records are appended to the file as they are inserted. So this is just like append only kind of thing. So this is the simplest of organizations. You don't have to think anything about it. You get a new record, go and add it at the end of the list of records that we have. That means you can keep a pointer to the last file block where it is in the disk, and then read that file block, add this new record, and write it back. Okay, so inserting a new record is done pretty quickly. You have to basically read the last file block, append this record and write back the block. But then locating a record given some values of any of these attributes would be a nightmare, because basically you just have to scan the entire file. You don't have any other means of getting hold of these records. So you have to scan the entire file. Now this kind of files are useful for organizing something like our some kind of unless there are other access structures, we rarely use this kind of a file organization. Okay. And this is typically kind of can be used in, for example, organizing the log data of some system, logging, as and when operations are happening, you just want to keep a log of what happened there. So you generate a log record and then keep inserting into the file. So most of the time you may not actually use the log. So if you want to actually use the log, then you can get hold of the thing and then search for the record. So you may be willing to pay the price for searching for a record in that search. But most of the time we don't use this shape file organization unless we actually also build other access structures that will help us locate the record. Okay. So the next one is very interesting organization, which is also called the sequential file or sorted file. So what we will assume here is that there is a field called the ordering field of the record that is chosen so that the records are sorted on that field. So the field on whose values are used for sorting the records in the data file is what is called this ordering field, and it could be in a key field, but it need not be a key field. Okay. So we call it ordering key field in case the ordering field is also a key. Otherwise, it is just called an ordering field. So basically, we store the file in the records are in the order of those ordering field values, and we call such a file as a sorted file or a sequential file. Now, what we can do here is given the value of this particular ordering field, locating a record is very somewhat easy. How do you do? You know that you can do if you are a sorted array and then locating a value in that, you will do binary search, right? So you could actually do some kind of binary search here. So locating a record given the value x of the ordering field, you can do binary search. But here you are doing binary search on the disk file. So what is the assumption here? The assumption, important assumption here is the address, the disk address of the nth block of the file can be obtained from the file header. So the file header has all the disk addresses, all the blocks. Okay, then you can do binary search. So you can pick up, so if it has 1000 blocks, so you can take out the 500 blocks address, and then you get 8 kilobytes of data or something like that. You get a block of data, and then you look for this particular ordering record which has this value x. And depending on the records that you get, if you are getting records whose values are much higher than x or much lower than x, you will have to appropriately move, do standard binary search. So decide whether you have to go to the upper portion of the data file or the lower portion of the data file, and then again ask for the make use of these file pointers. I'm sorry, the disk pointers that are available in the file header, and then get hold of the next file block and then keep searching like that. So what you do is about if there are n number of disk blocks, then about log n number of disk accesses would be required in order to get the block. So since log n is a slowly rising function, so this is reasonably efficient. So we will later on see how to improve this further. And range search is also efficient. So given two values, you can v1, v2, you can locate v1 first and then sequentially scan the file till you exhaust all the records which are whose values are between v1 and v2. So what about inserting a new record? Inserting a new record, there is a problem because the ordering might get affected, right? You have already ordered the file on roll number and it is there on the disk, and if you are very unfortunate, this new record that has to go will be in the very first block or something like, or first somewhere like in very first few blocks of the thing, and then you have exceeded the number of records that can be kept in block. So this the overflow block has to go into the next block, and so on. All blocks will get affected, right? So that's messy because if the file has 1000 blocks, then you have to put this fellow in 100 blocks. Then all those remaining blocks you have to read and write back. So this can be pretty costly. One technique you can adopt here is to actually not insert the data records into the data file at all. What you do is you insert them into an auxiliary file. Keep inserting the new records, whatever the records that come. And then the idea is, of course, after some time, so after several days of use of this file, then you can take some lean time off and then reorganize this file, insert all the records that are there in the auxiliary file into the main data file. So you can merge the auxiliary file and the main data file and then make the main file again into a sorted file. So if you are using an auxiliary file, then for locating a record, you first do a search on the auxiliary file first, because there are a fewer number of records there, and they'll probably be just fitting in a few blocks. So you will be able to quickly find out whether the new record, the record that is being requested for is there in that. If it is not there, then you go to the main data file and then do a standard search. Now, inserting a new record, we do it like this mainly because it might affect the ordered nature of the file. So is the case with the deleting actually. If you delete a file, delete a record, request comes for deleting a record, it might affect the order, right? So what you do, of course, you can just place a marker on that particular file, on that particular record, saying that that particular record actually has been deleted without actually deleting. Okay, so there will be in some sense an empty slot there. So it's marked as deleted, but you actually don't delete it. So if you the reason why you don't delete it is that if you delete and try to make the blocks compact or something like that, then again there will be a lot of movement among the blocks, and so which you want to avoid. So what you do is so both these techniques have to be used. You use an auxiliary file to keep inserted records as the file is in operation. Use auxiliary file to keep inserted records, and use deletion markers to mark deletions, and then periodically reorganize the whole thing, reorganize the whole scene, and then insert the auxiliary file records into the main data file, and ensure that all the marked up records are deleted and make the data file clean again. So when how often you should reorganize will depend on how often the file gets used in practice. Okay, so all that can be done. So on that particular ordering field, the access to the records is fast when you use sorted files. Okay, what about other fields? No use, right? Other fields, you basically have to do a file scan. Okay, so what you typically do is on the other, if we need access on the other files, so you build an index. You build an index, and then create a separate data structure using which you will then be able to find out a block address where the record is actually done. Okay. So the other thing, other primary organization is the hashed file organization. You have studied hashing in data structures, so I'm not going to repeat the details of hashing, but we will use the hashing idea and then use it for organizing the file. So this is a very useful file organization if we really want a very quick access to data records given the value of one single attribute, which is what we choose as a hashing attribute. So the hashing field is the attribute on which we want quick access, okay, and that is the attribute on which we perform hashing. So let's see how hashed files are organized, or how we use the idea of hashing to organize a file. So this is one of the primary organization methods. Okay, so the data file is we use a term called bucket in this context. A bucket is either a block or a few consecutive blocks. 2-3 consecutive blocks is called as a bucket. So the data file is organized in the form of buckets. So bucket numbers 0 through m-1 are used. Okay, and then we use a hash function. The hash function, what the hash function does is map the values of the domain of the hashing attribute. Some attribute we have chosen. So the values of the domain in the domain of the hashing attribute will be hashed by this hashing function into bucket numbers. So it will, so you give the value, it will give you a bucket number. Okay, so to insert a new record into this kind of a hashed file, what you do, so this is how the main data buckets, main data is lying here, and these are actually workflow buckets. So we'll see what exactly workflow buckets are. So each of these main file buckets can potentially have an overflow chain attached to it. Okay, an overflow chain will be like this. It's a pointer to one of the records, and that record has another pointer, etc. So that's an overflow chain. Okay, so why do we need overflow chains? We'll see that. So given some record, you have the value of the hashing field. So apply the hash function on this on that hashing attribute value, and then you get a bucket number. Go there to that bucket number. So these bucket numbers, where these buckets are, the disk pointers of all these buckets will be stored in the file header. So so bucket number I, you know the disk pointer, so you get hold of this bucket, and then go and insert. So there are two possibilities here. This bucket might be full. Okay, there is no guarantee that the hashing function actually distributes the records evenly, right? It might be skewed, you don't know, right? So this bucket actually might actually be full. If that is the case, then insert the new record into the workflow chain. If it is not, if there is some space here where you can, if there is a frame where you can put this, insert this data record, well and good, insert it. Otherwise, you chase this workflow chain, and then basically this is something like a buddy list, right? So you have you can take a free slot from here. You can take a free slot from here, put your record there, adjust this workflow chain to point to that, and then from that you can put a pointer to the next record that was there originally in the workflow chain, like splicing a new record into this workflow chain. So you can do that right in the beginning by using one of these free slots that are available in the workflow buckets. So you would have probably studied in data structures course as to how to maintain the free list, the available free slots can be can themselves be actually arranged as a list. So you can take out one item from that list and insert that frame into this workflow chain and put that record in that place. So that's how we can handle overflows into main data buckets. Okay, so the workflow chains of all these buckets are all maintained in this workflow bucket. Okay, so there in the file header there will be a pointer to the workflow bucket and the free list, actually the free list, so that you can, in case necessary, borrow an item from the free list, use it to put your record, and then adjust the free list. Okay. Now deleting record is also similar, because all that you have to do is to first use the hash function, then get hold of the locate the record which has to be deleted by applying this hash function. Then remove that R from the bucket and or the workflow chain, wherever it is. It's possible that, supposing there is no workflow chain, then it is there in the bucket, you can just remove it. If there is a workflow chain for the bucket, then there are two possibilities. The record might be here or might be in the workflow chain. So basically you will have to follow the workflow chain and then get hold of the record and then adjust the chain so that that record actually is not anymore there in the workflow chain. It is actually that slot can actually be spliced back to the free list. Okay. So that's how you need to do. So bring the record, yeah, if possible, bring the record from the workflow chain into the main bucket. That's also possible. Yeah, for example, if a slot becomes empty here, because of deletion, you might actually bring in the first record that is there in the workflow chain into the main bucket and then cut short the workflow chain. Because having a workflow chain is actually a burden. Right? So because you have to follow it. So search can be done given the hash field value k, compute this R, which is the hash of hash k, get the bucket R, and basically search for the record. Get the bucket. So the main cost is getting the bucket. That means get hold of those consecutive file blocks. And once you get them into your main memory, the searching is fast, so you can search. So if you are unlucky, then it is not there in the bucket, it is actually there in the overflow chain. Then you will have to really, that operation will be a little costly because you have to do several disk access. Okay, so on the average, you would have seen the analysis of hashing. On the average, you would only you would most of the time you will get your record in the main bucket itself. The overflow chains will be very small length overflow chains. If your hashing function is chosen in such a way that the records get hashed onto uniformly across the data buckets, and there is enough amount of space in all these main buckets, then the overflow chains will be small, if at all they are there. Okay, the length of the overflow chains will be small, and so most of the time you will get your data access, you will get your record the first time you access the main. Okay, so you compute the hash, the bucket number, and then go access that bucket. You are most likely to get the data. So that is actually pretty fast, because if you have organized your file to have say just 2 buckets per two blocks per bucket or something like that. So you're just making a couple of block accesses and getting all of your data record. In spite, irrespective of how many number of actual blocks are there in the data file. So this is one of the organizations that gives you very quick access to records, which if you have the value of the hashing attribute. Okay. Now, of course, there is a so basically now we have looked at what is called a primary file organization, which is the logical method by which we organize records into a file. Okay, and one of them is sorted files, the other one is hashed files. This particular hash file organization basically makes use of what is called static hashing. The problem with static hashing is that so we have assumed that the number of main buckets is in some sense fixed, right? So, but locating the positive thing is that locating a record given the value of the hashing field most often will happen in one block access, and the capacity of the hash file is something like if m is the number of main data buckets, r is the number of records per bucket, then this will be the capacity of the hash file. Now, if the actual file, actual records in the file, say you have designed it for some capacity, say you have designed it for some capacity, and you are expecting that many records to actually come into the file, and so you have designed it and kept it ready for use. The actual records that go into the file is, let's say, is much less than C, then there is going to be some wastage of disk space, because you have already allocated m number of main data buckets and kept that space ready for use. If the actual number of records is much more than C, then obviously the overflow chains will become longer, because you're hashing a lot more records into the structure than it was designed for. And so obviously main data file buckets will overflow, and so overflow buckets have to be used, and so overflow chains will be long, and so the data access will suffer. Okay. So data access will become costly. So these are the issues with hash files. So these are of course, similar kind of issues also are there with sorted files. Okay. So we have to look at organizations that can actually help us grow the file or shrink the file, and then the organization, can adjust itself but still give you a good performance. So that's another aspect we will see. If the file is not a static file, but it keeps growing and shrinking, how do we organize that kind of files? So static hashing is good for files whose size you have some good idea about, and then you don't expect more than say 10% or something like that excess records into the file. Okay, so in the next lecture we will see how exactly we can use this hashing idea and then make files dynamic, handle dynamic files and dynamic files. By dynamic files, what I meant is that you really don't have much idea about how big the file is going to become. So it might start small and then grow big, and then after some time it might actually shrink back to some row numbers of the large. If that is the case, how do you organize? Okay, so we'll stop here for today.